And this video is about antiderivatives. So, here we go. So we want to find a function, a capital F function, whose derivative is little f. Okay, so little f is 3x squared. We want to find basically the function who gives us that derivative. Okay, so using the knowledge that we have of derivatives, we can say that, okay, f of x must be, capital F of x must be x cubed, because I know that the derivative of x cubed is 3x squared. Okay, the function, that capital F, is called the antiderivative of little f. Okay, so a function f is an antiderivative of little f on the interval I when big F prime is equal to little f for all the x's in that interval. Okay, so we're just going backwards now from taking the derivative. We're starting with the derivative and finding the function. Okay, so note that f was called an antiderivative of f rather than the antiderivative of f. To see why, we can look at three different functions here. Let's let f be x cubed. Let's let f be x cubed minus 5. Let's let f be x cubed plus 97. Notice that all of these are antiderivatives of f of x equals 3x squared. Because if I take the derivative of x cubed, I still get 3x squared. If I take the derivative of x cubed minus 5, because that constant is 0, I still get 3x squared. Same thing here. That constant, any constant c added to x cubed, is going to give me an antiderivative of 3x squared. So what we're going to say is that if f is an antiderivative of little f on an interval, then g is an antiderivative of f on that interval if and only if g is of the form g equals f plus some constant, okay, where c can be anything. Now, using this theorem, we can represent an entire family of antiderivatives of a function, basically just by adding a constant to some known antiderivative. So, for example, say you know that the derivative of x squared equals 2x, right? That's obvious. We know that. We've studied derivatives. But now we can represent the family of all antiderivatives of f of x equals 2x. And this is basically just going to be taking this function and adding c to it, right? I know that any x squared plus anything will get me back to 2x when I take the derivative. Now in this case, anytime we add this c, and we're going to add c a lot, and you're going to forget to add the c, and you're going to get points counted off, but it happens. Be aware though that this c is called the constant of integration. Now the family of all these functions is called general antiderivative of f, and g of x is the general solution. When we have that plus c, that's called the general solution of the differential equation g prime equals 2x. So if I'm given that the derivative equals this, I want to look for the big G, right? And I know it's going to be in this form, and this is called the general solution. Now, this is called a differential equation because it is basically in a derivative form, right? We're saying that some derivative equals something. This is all differential equations are. So when we look at, and I know a lot of you have to take a class in differential equations, basically all it's doing is taking something that's got derivatives in it and trying to get back to something that doesn't. Okay? So this differential equation in x and y is an equation that involves x, y, and a derivative of y. And the whole point is to get back down to, well, what is y equal to? So in this case, y prime equals 3x, y prime equals x squared plus 1. These are examples of a differential equation. So let's actually do a problem. Let's say we have dy over dx equals 2. So I want to find the general solution of this equation. I want to find the y, because this basically means y prime equals 2, right? So I'm looking for, what is y? What do I need to start with? Well, what function gives me 2 as its derivative? Well, I know that if I take the derivative of x with some, 5x, 6x, 10x, negative 14x, all I get is the number in front of x, right? So I know that y has to be 2x. But I also know that it can have any constant added to it. And we can check this by saying, okay, well, what's the derivative of this? Well, the derivative of 2x is 2. So I know I'm on the right path. Now, if we graph all of these, you'll just see a bunch of things shifted up, shifted down. These are just all have a slope of 2x, all have a different y-intercept, right? Now, when solving a differential equation in this form, it's convenient to write it in terms of the differentials. Instead of saying y prime equals whatever, we can write it as dy equals f of x dx, okay? Now, the reason that we're going to do this is because we're going to be introducing something called indefinite integration. So the operation of finding all the solutions of this is called antidifferentiation, but more often we call it indefinite integration. And it's denoted by this integral sign. Looks like a weird elongated S. Okay? So the general solution is denoted by the integral of f of x dx, because the integral of dy is just y. Right? What gives us the differential dy? Well, y does. When we integrate y, we get dy. Same thing over here. If we integrate f of x dx, we get back to f of x plus some constant of integration. Okay? So, we're going to say that this says that this is read as the antiderivative of f with respect to x. Yes, it is, but more often than not, you hear it just termed the indefinite integral. Okay? Now, notice that dx tells us that's the variable that we're integrating with respect to, or that we're anti-deriving, right? So we know that our answer is going to have an x in it. So, if you have any questions about these, please just shoot me a reminder or ask a question in class.